Hi everybody, my name's Chris Collison and this is CHMP 442, Quantum Mechanics, Physical Chemistry 2 at RIT. So we are moving into week 5 of the course. You've just taken your first exam and we're going to learn a little bit from that. And before we move on to new material in this course, I want you to reflect and ask yourself the following questions. So have a look at this answer key that I'm going to be providing to you on my courses and ask yourself the following questions. So the first question is, could you answer these questions in that first exam well on a comprehensive final? So we will be having a comprehensive final. Some of these questions and some of the ideas in some of these questions are going to repeat. So this won't be the last time you see them. What we've learned so far are fundamentals and foundations of quantum mechanics that are going to see us through the next 9 weeks of the course. So can I answer this question well on a comprehensive final? Ask yourself that. If the answer is no, then come find me. Do I know what's going on? Quantum mechanics is particularly abstract, right? So ask yourself that question. If the answer is no, I'm not sure what's going on, come see me. Can you attend my office hours? There are many people in the same boat. This is complicated stuff. Please seek me out for assistance and we can go through things. So moving on to what we're going to be talking about in week 5 and the new material. So we're going to talk about, in this particular week and a half, we're going to be talking about the harmonic oscillator. So I've got a little arrow down here on the screen that you'll see. And when we think about the path that we've taken, we started right at the beginning thinking about a free electron. Then what we ended up doing is we talked about how we can confine that electron to our box. There's our particle in a one-dimensional box, and we expanded that to a particle in a three-dimensional box. What we're now about to embark on is we're going to go gradually into more complicated systems. So in this particular section, we'll go on to look at the harmonic oscillator. We'll later look at the rigid rotor, that's chapter 6. And then in chapter 7 and beyond that, we're going to think about the hydrogen atom. So the important thing here is to remember those foundations from the early weeks of the course. What are those rules that we've talked about? So number 1, we have to describe our system classically. Rule number 2 is we end up replacing the key observables with quantum mechanical operators. Why do we do that? Well, we need to build a Hamiltonian operator, and once we've done that, we can put that into our Schrödinger equation. Once we've developed the Schrödinger equation, then we need to solve the Schrödinger equation. We're going to find that as we move into the harmonic oscillator and the rigid rotor, those solutions become more complex. We're going to need help from outside. We're going to need to borrow some mathematics that was developed outside of quantum mechanics. And historically, that mathematics was already developed so that the pioneers of quantum mechanics could move forward without worrying too much about the mathematics. So we're going to take a similar approach. And then lastly, our 5th rule there is to apply boundary conditions. And so that's what we're going to do as we move forward with chapter 5. So what do we have set up in the lectures in this first part of chapter 5? Well, we're going to talk about that harmonic oscillator. We have to think about how we describe it classically. So we're going to use Hooke's law. We're going to use Newton's second law, F equals ma. We're also going to recognize that the potential, or work done, if you will, is equal to force times distance. So that's going to be helpful to us here as we think about the potential energy, the energy of our system classically. We're going to talk about conservative systems. That's the idea of someone on a swing and they start at a position of high potential energy. That potential energy is converted into kinetic energy as the child on the swing moves through the center point, and that kinetic energy is converted back into potential energy as they swing up the other side. This is called a conservative system. So energy changes from potential energy into kinetic energy backwards and forwards. The key here is that potential energy is a function of position. With our electron in a box, we were just considering the kinetic energy. So now we're adding this potential energy. So we're going to focus on balls and strings. We're going to use some wave equations, so classical simple harmonic motion to help us here. We're then going to extrapolate from a ball on a spring and think about diatomic molecules. And I'll talk about how we can use something called the reduced mass that allows us to consider diatomic molecules as if it was one ball connected to a wall, a fixed surface. Once we've done that classically, then that's where our rule number 2 comes in. Then we go quantum. We're going to add in our quantum mechanical operators. And at this point, as we go through these lectures, I want you to make sure that you read Math Chapter D in Donald Macquarie's textbook, and that would be pages 197 to 202. That talks about series in math. And then I'm also going to ask you to read through Chapter 5. So the course follows along with Donald Macquarie's book. Chapter 5 is very well written, and I'm going to encourage you to read pages 207 to 243. That's where the majority of the notes that I'm providing come from. So that will give you some reading to do if indeed the presentations here don't work for you as well as you would like. That textbook material will complement what we're doing in this class. So without further ado, we'll jump straight over onto the first lecture where we talk about the harmonic oscillator. Thanks for listening. So let's take a look now at the system we're going to be working with, and we have a ball on a spring. Here's our ball, here's our spring, and we have this connected to a wall in here, and we're also going to say at this point that there's going to be no gravity. So we're going to remove gravity from this particular situation. We have a equilibrium length. We're going to call that L sub naught. And because this is a spring, what happens is we get a compression when we push that ball closer to the wall. We can also imagine, again, there's no gravity here. We can imagine that when we pull on the ball and we pull it away from the wall, the spring elongates. And what the point here is that we've got this value L in here, and this value L is a varying quantity. It's the position. So let's make a note of that. So L varies. And here's our compression up here. And we will call this our rarefaction. In fact, maybe it's easier just to say that this is our stretch. So Hooke's law tells us that the restoring force, the force that pulls the ball back towards the wall, is a function of the displacement from that equilibrium length. So in other words, as we pull that ball further away from the wall, then the force on that ball is greater, right? There's more pull on that ball for it to return back to the wall. And so we can write a couple of expressions about the position. We can write some expressions about the restoring force. What we're going to start is we're actually going to define x in here. We're going to say x is equal to the position L minus the equilibrium length. And actually, we're going to say that x, we're going to define this as the displacement. So really, L is the length of the spring, but we're going to call x the displacement. It's the change in the length beyond the spring's equilibrium length. We're also going to talk about Hooke's law in a second. In fact, I'm going to go on to Hooke's law in the next slide here. Okay, so let's talk about Hooke's law in the next slide, but we're still referring to this system. So what is Hooke's law? We're going to say there's a force F. So here's our force. It's our restoring force. And as I mentioned, it's proportional to the displacement. So because it's a restoring force, the more we pull away the position of the ball from the wall, the larger the force. Okay, so we're going to say that because it's a restoring force, we've got this minus sign in here. So the force is equal to minus K multiplied by X. And K we're going to say is the spring constant, or the Hooke's law constant. And another way of writing this, by the way, of course, is we can also write it as minus K, and that would be L minus L naught. So we're writing it in a couple of versions in here, taking into account what our definition of displacement X is. So what we're also now going to do is recall Newton's second law, and that's force is equal to mass times acceleration. And we're also, what we've now described, of course, is we've got our force in here, but we're also now going to talk about the acceleration. So ma is our force. So mass times our acceleration. So we have a mass of the ball. So force. So according to Newton's second law, F is equal to ma, which is equal to the mass, and we're going to write it in terms of L at this point. So that'll be d squared L by dt squared. So what we recognize here is that this is the second derivative of position with respect to time. We can also recognize, by the way, that this would be equal to m d squared x by dt squared. Why is that? So remember, of course, that dl squared, or d squared L by dt squared, is really the same as x plus L naught over dt squared. But we recognize that with L naught being a constant, the second derivative of a constant is actually going to be 0. So that, of course, is equivalent to m d squared x by dt squared. So that's how we get this expression. We also recognize that that force, it is the restoring force, and that ends up being equal to minus kx. And the next thing we're going to do is we're going to rearrange this expression in such a way as I will show. So we're going to bring the kx over to the other side and make that equal to 0. And this, in your textbook, by the way, is equation 5.3, and that's on page 208. And we're going to consider that there is a general solution. We've come across this kind of equation before, so we're going to say there's a general solution, and the general solution is x, remember it's a function of t, equals some constant c1 sine omega t plus c2 cosine omega t. We've seen that general solution before. So x is a function of time. I'm also going to introduce at this point the omega term, and we're going to say that omega here is equal to k over m. We're going to take the square root of that, and to continue with our treatment here, we're going to imagine stretching this particular ball on a spring to its maximum displacement, and that maximum displacement will be A. So we're going to say that's our amplitude, is our maximum displacement, that is A. What else can we say? Okay, so what we're going to do now is imagine a situation where we pull the ball to its maximum displacement, and that's going to be at time t equals 0. And we're also, from the previous slide, we're going to recall and remember our general solution. And what we're going to do in this next step is just refine that solution. So we think at t equals 0, what do we know about the displacement? Well, we know that x at time t equals 0 is equal to that amplitude A. We also know, in general, when we are considering, even a buoy on a swing or the ball in simple harmonic motion, when we've pulled the ball to its maximum displacement, the velocity is 0. There's a turning point. The same thing goes at time t equals 0. So what we're going to recognize here is that the velocity dx by dt at t equals 0, that is also equal to 0. There's our velocity. Okay, so this is our velocity. So now we're going to consider our solution, right? So here's our general solution. Of course, we can write this down. X of 0 is equal to C1 sine omega t plus C2 cosine omega t. When t is equal to 0, of course, this expression will also be 0. And when t is equal to 0, of course, our cosine term is going to be equal to 1. So that tells us that what this means is that since x of 0 is equal to a, then what this tells us is that C2 must be equal to a. And that's our amplitude. So C2 is our amplitude. The next point we'll bring up, we'll do the same thing with dx by dt, our velocity, at time t equals 0. And that, of course, we've said was equal to 0 at t equals 0. So we're going to take the derivative, of course, of the function that we started with. We're going to take the derivative of this function in here. So that gives us C1 omega, and now cosine omega t, minus C2 omega sine omega t. Okay, so there's the derivative of that function. What else can we say? Well, of course, we also recognize now that when t is equal to 0, cosine omega t is going to be equal to 1. So this expression in here is equal to 1. And again, we've got our sine omega t term, and that's equal to 0. So we're going to find that this second term is going to cancel out because of that 0. And what we also recognize now, of course, is that C1 omega is equal to 0. So the only way this can happen, of course, because omega is equal to the force constant k divided by m, the square root of that. So we looked at that in the previous slide. So the only conclusion here is that C1 must be equal to 0. So what does this allow us to do? So remember up here, our goal here is to refine our solution. And so therefore the refined and the final solution can be written as x of t is equal to capital A cosine omega t. So what does that look like? So we can actually draw the plot there of that particular curve. So let's change colors here for a second. So we have a cosine wave that goes from plus a as our amplitude to minus a. And so here's the solution. And we recognize, again, this is our amplitude. And here is our plot of the wave. And also, just for the record, let's remind ourselves that the angular frequency there is equal to 2 pi nu, which is the frequency. It's also radians per second So this is the angular frequency, and it's in radians per second. There's the units. Okay, so that this concludes section 5.1 of Donald Macquarie. So let's now move on to start thinking about the force and the potential, and we'll try to tie that all together. So we're now going to launch into section 5.2. We're going to continue with a classical description of our harmonic oscillator. We're going to call this our ball on a spring. We're going to recognize that it is a conservative system, and a conservative system is much like, you know, here's our little girl on a swing, and the little girl on the swing sort of moves backwards and forwards. Okay, and at the top of the swing, she has maximum potential energy. And when she's in the midpoint on that swing, she has maximum kinetic energy. But effectively, the energy is conserved, and that's why we're going to refer to this as a conservative system for our ball on a spring. So let's first think about the force, and we're going to call this, actually we'll call this little f of x, and the force is a function of x, and we've of course already described what that force is in terms of Hooke's law. So f of x is equal to minus kx. But looking at this from a perspective of classical physics, the force is equal to minus dv by dx. That's potential is the v, and of course potential is equal to force times distance if we think about that in the simplest physics terms. So let's make sure we make a note of that. V is the potential. And so what do we do with this now? So let's actually take our force. Let's recognize that v of x is equal to minus the integral of f of x with respect to x. And again, we've got our Hooke's law expression, so we're going to simply plug that into here and do that integration. And what do we get? Well, we will get v of x is equal to, and it'll be plus kx squared. So we've got a minus in here. Don't forget, here's our minus, but we've also got a minus value in here for f is equal to minus kx. So we end up with plus kx squared over 2 plus the integration constant. So we're going to also say that v of x, by the way, is equal to 0 at the equilibrium position. So here's that equilibrium position here. It's also the same as here's our ball, okay, on the spring. There's our ball on the spring, and there is this equilibrium position. So we're at L0 in here. At that point, the potential is equal to 0, of course, and we're going to say x, remember, is equal to 0 because L minus L0 is equal to 0, so that's x, of course. So we're going to say v of x is 0 at equilibrium, and therefore we're also going to say, that c equals 0 for an undistorted spring. Let's remind ourselves of the solution that we have from the previous slide. So of course we've got x of t is equal to a cosine omega t. We can also write down here dx by dt, and that's going to be equal to minus a omega sine omega t. Okay, so that's going to be important. So that was our potential energy. Let's stay with green here for a little bit, and let's remind ourselves now of kinetic energy. So that was potential energy up here. So now we've got to think about kinetic energy. It's always the same in physics. It's half m v squared, or p squared over 2m, another way of writing it, same thing. Remember, what is velocity? Well, velocity is the first derivative of position with respect to time. Okay, so we've got our velocity in here, so this is our velocity. Okay, so this is equal to half m dx by dt squared. So note we are squaring the derivative here. We're squaring the result of that derivative because we're squaring velocity. This is not a second derivative in here, so we've got to make sure we're clear on how we write these things down. So let's round this out and say that kinetic energy is equal to, well, we've got this mass over 2 in here, and then we've got the second, or the first derivative here, minus a omega sine omega t. So the minus times minus becomes plus, the a squared, the omega squared, and then of course the square of sine omega t is sine squared omega t in here. And so this ends up being our kinetic energy term. So what we can also do, let's change colors again here. Let's go to blue. Okay, because we got our kinetic energy, we can now think about that potential energy, which is this is the V term that we care about, V of x, and that we found was equal to, up here we've got kx squared over 2, but we know what x is. Okay, so we can plug that x in, and we find that we're going to end up with, instead of plus k x squared over 2, we got plus k over 2 multiplied by a squared cosine squared omega t. Okay, and now in the next slide we're basically going to remember that total energy, so we'll call that E total for now, is equal to E, we'll just use the kinetic energy plus potential energy in here. Okay, so what we're going to do is take these values and add them together in the next slide. Okay, and I'll rewrite that for you. So E total is equal now to, here is our kinetic energy, so it's m over 2a squared, and that's k over m. Why k over m? The k over m comes from the omega squared, by the way, which is equal to, well, omega is equal to k over m to the half. So we square that and we end up with k over m in here. So sine squared omega t. And then the potential energy term is k over 2a squared cosine squared omega t. Okay, now where am I going with this? What's a very easily remembered trigonometric identity that we are going to pretty much use? Well, we use this all the time. We should remember this all the time. Sine squared theta plus cosine squared theta is equal to 1. Okay, so effectively here we've got sine squared omega t and cosine squared omega t is equal to 1. We're going to combine these together. Very simple algebra in here. And we are going to, well, by the way, over here we can cancel the m's. Okay, so we're going to end up with a k over 2a squared. In here we've got k over 2a squared in this term. And we've got a k in here over 2a squared in here. So what I calculate this to be is k a squared. So we've got k a squared over 2 plus k a squared over 2. It becomes k a squared. And so what are the implications of this? The implications are that the total energy is a constant in this system. And we're going to say that the harmonic oscillator is a conservative system. It's a definition that when the energy is conserved within the system, we will say that it is a conservative system. So what else am I going to say in here? A couple more things just to tie up some loose ends in here. The force is a function of only the spatial coordinates describing the system. Okay, so I'm going to write down a few equations here. We'll tie it all together. I'm going to introduce a new term to you in a second. So That's the point of this v of x, y, z, okay, is what we're going to consider. Let's suppose we've got, change color again, f sub x. Let's suppose that's a function of x, y, and z. So remember, the force is a function of the spatial coordinates describing the system. Okay, so it can be a function of those spatial coordinates, the position x, y, and z. That is equal to minus the partial derivative di v by di x. Similarly, the force f sub y is also a function of the spatial coordinates, the position of the system. Okay, that's equal to minus di v by di y. And you guessed it, f sub z is the force that is a function of the position, the spatial coordinates x, y, and z of the system. That's equal to minus di v by di z. Okay, and from that we are going to recognize the force as a vector quantity, x, y, z. Remember, it's a function of those coordinates x, y, and z. And because of this vector notation, we are going to write this down. And this may seem familiar to you. We've got a del in here, but it's a del with a little arrow on the top. It's a vector term. So del v, x, y, z. And the point that what I'm introducing you to in here is that we're going to say that del in here with the little arrow on the top is what we called the gradient operator. And that del, how do we write that del with the little arrow over the top? And that's equal to, we're going to have these unit vectors in here, I di by di x plus j is a vector, the unit vector di by di y plus k unit vector di by di z. And so that is what we call the gradient operator. So the point of this was simply an intro to notation in here. Okay, and that was really this piece that I'm describing down here. Everything else above it, yes, we've got a conservative system in here. And we've also connected potential energy and kinetic energy. And of course, that's what we're going to need if we want to solve our Schrodinger equation, to talk about a quantum mechanical system that looks like this ball on a spring. So that's where we're going next. So now we're going to talk about harmonic oscillators in chemistry. And really, as we think about this ball on a spring tied to a wall with no gravity, how does that at all relate to molecules? And in fact, harmonic oscillators in chemistry are best described when we have a hydrogen chloride molecule, for example. We have two masses. We have a mass M1 and a mass M2, and they're connected together by this bond. So in the diagram that I'm showing here, I've got an x-axis in here, and I've got the position of the first atom, let's say, of mass M1. The position of that mass is at position x1 on this x-axis. So in other words, its number, its location, its coordinate is x1. And then we have a second atom in here, with mass m sub 2. So these are masses m sub 1 and m sub 2. And that second mass is located at position x2. The important thing here is that these positions are going to vary. X1 is going to vary and X2 is going to vary. And we've got two balls, in other words, and we're going to have two equations of motion. So let's talk for a second about what those equations of motion are. And we can immediately jump to F equals ma. Okay, so we can start by saying, well, m1 times the acceleration is, of course, the second derivative of the position with respect to time. And we've also equated this, so F equals ma, we've equated this to the force associated with Hooke's law, right? So the Hooke's law force is going to be equal to K. So that's the Hooke's law constant. It's a plus K. multiplied by, in this case now we're going to have the relative positions x2 minus x1 minus L0. Okay, so this is the relative position because the spring goes between mass m1 and m2, and L0 of course is the equilibrium length that exists between these two balls. So this still ends up being the equilibrium length L0 between those two masses. In fact, you could also say that x2 minus x1 is like the value L that we had in our previous description. What we can also say, of course, is that for mass m2, as I said, we've got two equations. That's equal to plus, well, it's actually going to equal to minus k this time. It's minus because, don't forget, in this direction we can have a plus value. If it's in the other direction, we can have a negative value. So when we pull that particular ball in a different direction, that means that we're going to have the minus sign in here. So that ends up being x2 minus x1 minus L0 again, and let's just recognize it's the same as that L from the previous description. So what are we going to do with this now? So we've used Newton's second law. We're actually going to use Newton's third law next. Let's jump to this next slide where I've got it written out. Newton's third law, of course, is the force on M2, by the way, is equal and opposite to the force on M1. How can we write that down mathematically? Let's do that. So again, we've got M1 d squared x1, so it's the second derivative with respect to time, of position with respect to time, that's ma. So plus m2, so force is equal to ma, right? So these are forces I'm writing as the terms on the left hand side of this expression, and we're going to say that according to Newton's third law, they're equal and opposite, and therefore they sum to be 0. So that's the force on m1, and here's the force on m2. Again, where are we going with all this? We're gradually going to get further and further away from the starting point, but let's remember that starting point, right? We're trying to say we've got these two atoms connected together, and we're trying to understand how that relates to a single ball on a spring connected to a fixed wall. What we're also going to do here is now we're going to say, I'm going to introduce capital M in here. So capital M is equal to M sub 1 plus M sub 2. And I'm going to give you a little bit of rudimentary physics. Let's just, for example, think about this molecule, if you will, on a fulcrum. We've got a mass, is our mass M2, mass M1, and the position with this molecule laying flat, okay, tipping neither one way nor the other. That means that the fulcrum here must be at the center of mass. I'm going to call that x sub m for the time being. Later on, by the way, I'm going to say that x sub m is going to be equal to x. I'm going to capital X in here. But for now, we'll keep it as so, and we're going to recognize these positions. This position here is x sub m minus x sub 1. Remember, the position of mass m1 is x sub 1, right? And the center of mass isn't necessarily in the middle, okay? But it's these distances that are important. So this distance here, for example, is going to be equal to, what would you say, x2 minus x sub m, okay? So we can also recognize that because this is balanced, let's change color here for a second. So because this is balanced, we've got m1 multiplied by x sub m minus x sub 1 is equal to m sub 2 multiplied by x sub 2 minus x sub m. So what we now do is expand these brackets and collect the terms. I'll let you do that. But after we expand and collect terms, we're going to end up with on the left hand side, m1 plus m2. Remember, we've got m1 times xm, and we've got m2 times minus xm on the other side. So when we expand those brackets and bring everything over, we get m1 plus m2 multiplied by xm equals m1 x1 plus m2 x2. This is where now I'm going to remind you of what I said earlier. I'm going to say x sub m, we're going to call capital X. And what I'm going to do, I guess, this expression, I guess, let's replace this in here with the capital X in here. And let's rewrite this expression now. So we've got X is equal to m1 x1 plus m2 x2 divided by, well, we've also expressed that m1 plus m2 in here, that is equal to capital M. Okay, so we've got this piece up here I've described already. So capital M is the total mass. So we're also going to recall, of course, we're going to simply bring those masses. We can do this because the mass is constant, but we're going to rewrite this as d squared m1 x1 by dt squared plus d squared m2 x, so that's x1 there, and x2 here by dt squared. Okay, so we know that that's equal to 0, right? We remember that's equal to 0 according to Newton's third law. But we're also going to write this down as now, and again I'm going to change color. Let's go back to red. That is equal now to d squared by dt squared, and inside the brackets here I'm going to write m1 x1 plus m2 x2. This actually works as well, drawing on something from the past, because that d squared by dt squared operator is linear. Okay, so we can do that, and that value of course is equal to 0. So this is equal to 0 because of Newton's third law. What else? Now I'm going to move things around a little bit. I'm going to bring the m over here. Okay, in fact, let's make this easy. Let's keep this all on the right hand side, give ourselves a little bit of space. Okay, so I've got this expression now, m1 x1 plus m2 x2 is equal to capital M multiplied by the position of the center of gravity. Okay, so this term is equal to d squared mx by dt squared. Okay, so this expression in here is equal to this mx up here. So what are we left with? Let's kind of simplify again. Let's just change color. So we're left with m d squared x by dt squared is equal to 0. Now we've also we've recognized, of course, that F equals ma, which is equal to Hooke's law. So we also know, by the way, that m d squared x by dt squared plus kx is equal to 0. So the thing is, there's no force term in this expression over here. We'll come back to this. What's the point? What's the point of this? So I'm going to let me state the point in the next slide. So the point, we have a single center of mass which moves uniformly with time with constant momentum. What else? So really, these are points to take note of. So I'll just say note in here in the column on the side. What else? We're also going to recognize another point. Vibrational motion must depend on relative separation of the two masses. of the two masses, and this is called the relative coordinate. Okay, so we're going to use the relative coordinate later. If you think about it, we don't really want to be thinking about the positions of two masses. We might want to think about the relative coordinate, the relative position of the center of mass, thinking about one ball on a spring connected to a wall. So we're going to consider that in the next next piece here. So let me just express again that x is equal to x2 minus x1 minus L0. Okay, and earlier, we've expressed that we had m2 d squared x2 by dt squared. So that's our Newton's second law piece, and that was equal to minus k, and we've got x2 minus x1 minus L0 inside the brackets. Now, of course, we can do the same thing for m1 d squared x1 by dt squared equals plus k. So this will seem familiar to you. X2 minus x1 minus L0. What we're going to do here, actually, I can do this very simply. I'm going to take the m2 from this side in here and the m1 from the left hand side here. I'm going to put it back on the right hand side. Okay, so I'm not going to do anything crazy in here mathematically, but this is m2 in here and m1 in here. And what I'm going to do is, let's call this equation number 1 and let's call this equation number 2, and we're going to subtract equation number 2 from equation number 1. So we end up with d squared x by dt squared minus d squared x1 by dt squared, and that's equal to minus k 1 over m1 plus 1 over m2. Okay, and in the brackets here, x2 minus x1 minus L0. Okay, so we've separated, we're subtracting one equation from the other, hence we get this 1 over m1 plus 1 over m2 term as a second factor on the right hand side. So for this final piece, what we're going to remember is our definition, first, of what x is, and second, we're going to remember this 1 over m plus 1 over m1 plus 1 over m2. So we're going to look at that first as we go to the next slide. So of course, 1 over m1 plus 1 over m2, well, we're going to multiply the first fraction by m2 over m2, so we end up with m2 over m1 m2 plus, over here, we're going to multiply by m1 over m1, and this of course ends up giving us m2 plus m1 over m1 m2, and this value ends up being 1 over what we call the reduced mass. The reduced mass is mu in here, so let's make a note of that. So mu is called the reduced mass, and as I mentioned before, we're going to let that x equals x2 minus x1 minus L0. That's our definition. So where were we before? Let's write down the equation that we had from the previous slide. We remember we had this d squared x2 by dt squared minus d squared x1 over dt squared, and that was equal to minus k 1 over m1 plus 1 over m2, and of course now that we can replace, I'll replace that in a second. So let's replace everything over here. For example, this ends up being equal to 1 over mu.
In fact, let's write the k up here, so minus k over mu. And then we've got this x term in here, right? So this becomes our x based on our definition. And over on the left-hand side, we're going to write this down as, don't forget, if we take the derivative of this expression here, in fact, if we take the second derivative of this expression, we, again, because the operator d squared by dx squared is linear, and also if we remember we take the derivative of a constant, we're going to end up with 0. So what we can recognize in here is, I'm going to write it as d squared x2 minus x1 minus L naught by dt squared. That equals minus kx over mu. So we can do that, as I've just explained why. And so what we've come to here finally is we've got a d squared x by dt squared equals minus k over mu times x. And actually let's go one step further and make this mu d squared x over dt squared. We're going to bring the plus kx, so we're bringing this over the other side, and this expression now equals 0. And what we're now going to recognize is if we go back and we think about the expression that we derived for the ball on the spring, right? So the ball on the spring, we came up with a situation that was m times dx by dt squared plus kx. That was equal to 0. So in red here, this is for the ball on the spring connected to that fixed wall. We find that this expression is identical in form to the situation that we've described for our molecule, right, where we have two balls connected to each other. The difference is, and how do we relate here? Well, when we have two atoms in a molecule, we have to use this reduced mass term in here. We now know what the reduced mass is. We can measure it from the masses of the two atoms in the molecule. But the point here, the final point of all this is identical to the one body problem. And the whole point of this was to simplify our molecule. It was something like a hydrogen chloride gas. Okay, we've simplified our molecule with two bodies, and we've basically said that the simple physics describing a one body ball on a spring is the same as for our molecular system, our diatomic molecule, as long as we used this reduced mass. And that is really important because now we're at a point where we can move forward with quantum mechanics. We have a simplified ball on spring type expression that we can plug our operators in for this particular case and start building up our Schrödinger equation. So that's it for this particular lecture. What we've done is really just expanded. We've spent the whole lecture talking about the classical mechanics behind a ball on a spring. We've said that it's the same as a diatomic molecule, and now we're going to move forward and think about how that translates into a quantum mechanical problem. So thanks for listening.